Hi, welcome back. In this lecture, I would like to talk about an application of the CNOT quantum gate on a superposition of state. So we will have a two-qubit system, we bring it to a superposition of state, and then we apply CNOT on a control qubit that is in a superposition. This quantum circuit will give us the so-called Bell pairs qubits, and also will be our first encounter with a quantum circuit that produces entanglement. We saw in the previous lecture that there is nothing particularly quantum about the CNOT. It's just a conditional logic that is also a fundamental feature of any conventional CPU. We saw, for instance, the if constructs also on CPU. But in this lecture, we tackle a question that is particularly interesting. So what happens if the control qubit of a CNOT operation is in superposition? So let's look at this. To do that, we can prepare the so-called Bell's quantum circuit with two 1-qubit register A and B. The results of this measurement is called the Bell pairs. We will see that one extremely striking part is this measurement on the 2 qubits is random, but these two values will always be the same. So the Bell pairs is basically working in these ways. We initialize our system, for instance, in state 0, and then we bring the qubit that is the control NOT for the control qubit for the control NOT operation. We bring this to a superposition of state using the Hadamard. And then the target qubit is the second quantum register B. What we have to remember here is that this part of the circuit, we put the control qubit in a superposition of state. So let's look at each step of the Bell circuit using the circle notation. The first step is actually to initialize the 2 qubit system in the 0, 0 state. So we put the first register in 0, the second register in 0. If we represent this as a 2 qubit system, this corresponds to initialize our 2 qubit system in the state 0. The second step is actually to apply the Hadamard gate on the first qubit. So the results of this operation only on the first qubit is here the following. So we can still think in a way of circle notation. So the step is the so-called conditional NOT, where the control is on the first qubit, the register 8, and the target is the second qubit, the register B. So this is the results of our superposition, and then we apply a control NOT. So the target is on the second qubit, so we can identified the pairs that we're going to act on. So this is the first pair, and this is the second pair. And this is because we have the NOT on the second qubit. So there is a stride of. Remember then that the CNOT is a selective NOT operation. So we're going to make that NOT operation only on those states where the first qubit is in state 1 in the binary notation. So this is 0, 0, 0, 1, and this is 1, 0, and then 1, 1. So we care about, in this case, the first qubit, that is the control. So this is going to be only this and this have 1. So this means that the only NOT operation is this one that we do. right? So there is a condition on the first qubit, it must be 1. So this is not occurring, only this one. So the results of this CNOT operation is actually the following. Something similar we saw in one of the lecture of multi-qubit states, and we saw that something like this was actually an entangled state. So this is the results is a superposition of 0 and 3. This actually makes sense since if a qubit had taken value of 0, then no action will be occurring on B. Remember that qubit A is the control qubit and would remain in the state 0, leaving the register in a total state of 0. So if A is in 0, nothing happened. However, if a being in state 1, then the NOT would be applied to B, and the register would have value of 1, 1. That is actually 3. Let's dive in the concepts of an entanglement. So this circuit is called the Bell circuit. The major characteristics is that we have a control qubit that is in superposition. This Bell circuit has the important capability of producing an entangled quantum state. So this entangled state demonstrates a kind of interdependence between the two qubits, the qubit A and the qubit B. It turns out if we read out of the qubits, although the outcome will be random, the values for the quantum register A and the value of the quantum register B will always be agreed. This also means that we can just measure one and automatically we will know what will be the results. Keep in mind that if we take a 1 qubit and we measure either state 0 or 1, this will still be random. What is the entanglement effect includes is the fact that if we read one register is a random value, either 0 or 1. We do the measurement, we get either 0 or 1, and the entanglement will ensure that also the measurement of the other register will be the same. So still random, but there is this strong interdependence with the other register. So using Bell pairs has been an important feature for implementing shared randomness. So we note that measuring a single qubit superposition provides us with a quantum random number generator. So just applying a Hadamard gate and a measurement, having a measurement, this is a random number generator. Similarly, the reading out the Bell's pair acts like a quantum random number generator, only now that we will obtain 2 qubits that always will agreeing on random values of the qubits. A surprising fact about the entanglement is that the qubits involved remain entangled no matter how far apart they might move them, right? So there is this independence. Once we generate, it will be forever. It will be interdependent. So if you measure one, we also will know what is the other one, the values of the other one. In this way, we can easily use Bell's pairs to generate correlated random bits. So these are bits that are random, but are strongly correlated to the same value of the other quantum bit. And we can generate correlated random bits at different locations. This shared random mechanism is at the base of establishing secure shared randomness that, for instance, can be used for communication, quantum communication. These are the last slides of this lecture, and talk to you soon.